I'll explain how the components of a zinc Coppervoltaic cell interact to generate electrical energy. In a zinc Coppervoltaic cell, a spontaneous oxidation-reduction reaction is compartmentalized. During the process, zinc metal will lose electrons by a process called oxidation, and aqueous copper 2+ cation will simultaneously gain electrons through the process of reduction. The components of a zinc Coppervoltaic cell includes two half cells, where each half cell contains a different electrode. In the half cell on the left, the electrode is zinc metal. In the half cell on the right, the electrode is copper metal. Each half cell also contains an aqueous solution. In the half cell on the left, the aqueous solution will be 1 molar zinc nitrate. In the half cell on the right, the aqueous solution is composed of 1 molar copper 2 nitrate solution. The two electrodes are connected by wire through a device called a voltmeter, and the circuit is closed by use of a salt bridge, where in this particular case a salt bridge will contain 1 molar sodium nitrate. In a functioning zinc Coppervoltaic cell, several processes will occur simultaneously. For example, at the zinc electrode, zinc metal will undergo oxidation, releasing 2 electrons and aqueous zinc 2+ cation. During the process, the zinc electrode is essentially dissolving. Therefore, the zinc electrode will become smaller in size. Since oxidation occurs at the zinc electrode is called the anode and is assigned a negative charge. The electrons released through this process will travel through the voltmeter, generating a voltage of 1.10 volts to the copper electrode. At the copper electrode, aqueous copper 2+ cation will undergo reduction. This will form copper metal, which will plate onto the copper electrode. During the process, the copper electrode will increase in size. Since reduction occurs at the copper electrode is called the cathode and is assigned a positive charge. In a voltaic cell, the salt bridge prevents polarization between the two half cells. During the process of oxidation, zinc 2+ cation is produced. The net charge in each half cell must be 0. To cancel the excess positive charge due to the zinc cation, negatively charged nitrate anion will migrate into the half cell. At the half cell containing the cathode, positively charged copper ions are being removed from the solution. This will leave negatively charged nitrate anions remaining in the solution. To counter the negative charge due to the nitrate anion, initially positively charged sodium cations will migrate into the half cell. Remember, the solution in the salt bridge will be 1 molar sodium nitrate. After the sodium cations are completely consumed from the salt bridge, positively charged zinc ions will now migrate from one half cell to the other half cell. The net effect of the salt bridge will be to maintain an overall 0 charge within the voltaic cell. As with the sodium cation, the nitrate anion that is associated with sodium nitrate will eventually be consumed. At that point, negatively charged nitrate anion will migrate from the half cell containing the cathode to the half cell containing the anode. This overall process will maintain a net charge of 0 within the voltaic cell. In a functioning voltaic cell under standard conditions, the reading on the voltmeter should be 1.10 volts. However, this value may also be determined mathematically. Using a reduction potentials table where a positive value indicates a likelihood for the process of reduction and a negative value indicates that reduction is not favored, we see that the reduction potential for copper 2 plus cation is positive 0.34 volts. Comparing that value to the reduction potential of zinc 2 plus cation, we see that the value for the zinc 2 plus cation will be negative 0.76 volts. These values indicate that the likelihood for the copper 2 plus cation to undergo reduction is greater than that for zinc 2 plus cation. Indeed, in a functioning voltaic cell, zinc metal will actually undergo oxidation and copper 2 plus cation will undergo reduction. The value indicated for the reduction potential for zinc 2 plus cation represents in magnitude the oxidation potential for zinc metal. The oxidation potential for zinc metal will be a positive 0.76 volts. To determine the overall cell potential, indicated as E cell, where overall cell potential is equal to the oxidation potential plus the reduction potential, we see that by adding the two values, 0.76 volts plus 0.34 volts will equal 1.10 volts. Under standard conditions, the overall potential or energy generated in any voltaic cell may be determined mathematically using a reduction potentials table. As a point of fact, one should remember that although in a zinc coppervoltaic cell, electrons will flow from the zinc electrode to the copper electrode or from the anode to the cathode, the actual direction of current flow is the reverse. Current flow is defined as the direction in which positive charge flows. Obviously, in this case, negatively charged electrons are flowing from left to right. This means that, by default, positive charge is flowing from right to left. This concludes my explanation of how the components of a zinc coppervoltaic cell will interact to generate electrical energy. Hopefully this video has been helpful. Thanks for watching.